A very good day I bid to Dr. Azmi as our lecturer for this BRG 4783 wireless communication systems. So today our group will be presenting our assignment titled Performance Comparison of FDMA and TDMA, CDMA and OFDMA. Our group members starting off with me, myself, Jashila Chelias, followed by Sasitan Sankar, Nur Izelia Natasha, Pavitran Rajendran and Rukinis Swari Pakim. So for the introduction part, we start off with our introduction for our assignment. So FDMA stands for Frequency Division Multiple Access. It is a robust against varying channel conditions, provides stable performance. TDMA, on the other hand, Time Division Multiple Access, excels in information freshness, minimizes AOI, ideal for time-critical applications, whereas CDMA, Code Division Multiple Access, it is useful in high spectrum efficiency and can be able to handle multiple users on the same frequency. OFDMA, on the last but not least, means orthogonal frequency division multiple access, enhances spectral efficiency through subcarrier multiplexing. Thus, it is suitable for high data rate applications in 4G and beyond. So how does it integrate with modern networks? Well, multi-carrier waveforms paired with OFDMA improves service quality, thus enables efficient use of the available spectrum. But all it is good, but there is some present challenges and considerations where increased signal processing complexity, thus potential for inter-symbol interference in some configurations and cases. So what are the key factors in choosing an access method? Well, the key factors were application requirements such as latency, error rates, and channel conditions. So that is for the introduction for our assignment. Now we go into the objective, why we conduct this assignment. We have divided our objective into three sections. First, spectrum efficiency, flexibility and scalability, and cost and complexity. So first, spectrum efficiency. To access how effectively each technique utilizes the available frequency spectrum for multiple users to share the same frequency band simultaneously under unique codes. Whereas the cost and complexity, it is used to evaluate the cost implications and technical complexity of implementing each method. Last but not least, flexibility and scalability, it is to determine the adaptability of each technique to varying network demands and applications. That's all from me. I pass this presentation to the next person.
As for the problem statement, FDMA, latency optimization in hybrid NOMA FDMA system for dual computation offloading, has a high density network challenge. Traditional FDMA system face difficulty in achieving optimal latency in high density environments. Second, resource allocation limitation. Inefficient resources allocation mechanisms further exacerbate latency issues in such networks. The third will be potential of hybrid integration. Combining NOMA with FDMA enables dual computation offloading, offering a potential solution to minimizing the latency. The fourth will be the increased complexity. The integration introduces challenges in managing the interference and ensuring the efficient resources allocation. The resource allocation challenges in IRS-assisted wireless-powered FDMA IoT networks are IoT needs high energy efficiency and reliable communication. FDMA limitation are traditional FDMA struggles with resource allocation and adaptability. So the IRS and wireless power, using IRS and wireless power transfer can improve the efficiency and coverage. The key challenges are, it is still hard to allocate resources efficiently in FDMA powered by IoT networks. So for the TDMA, enhancing tracking accuracy in TDMA-based acoustic indoor position systems, traditional TDMA struggles in high-density vernacular network due to scalability and efficiency issues. The problem is to optimize a hybrid distributed centralized TDMA approach for better performance in these dynamic environments. Optimizing TDMA performance in high-density vehicular networks, TDMA-based indoor positioning systems often suffer from errors in slot allocation, reducing tracking accuracy. The problem is to create a better error correction method to improve time slot allocation and overall system accuracy. So for the CDMA, enhancing MCDS CDMA performance in LEO satellite networks. LEO satellite networks using multi-carrier direct sequence CDMA, MCDS CDMA face significant challenges due to co-channel interference, which is a CCI, and suboptimal power control. The second would be the problem is design effective CCI, mitigation and power control strategy to optimize system performance and ensure the reliable satellite communication. So to improve efficiency in an OLOD CDMA system often struggle with high decoding complexity, leading to increased latency and power consumption. The problem is to develop a low power complexity decoder that simplifies the decoding process while maintaining the efficiency and performance in synchronizing the CDMA system. For the OFDMA, optimizing resources management in downlink OFDMA networks. The downlink cellular OFDMA networks face challenges in managing load, power, and emission control efficiency. Improper resources allocation can lead to reduced drought and the energy efficiency. The problem is to design effective strategy for load management, power control, and emission control to optimize overall network performance. So improving the accuracy in uplink IM OFDMA system. Uplink OFDMA system suffer from performance degradation due to in-phase and quadrature IQ imbalance, which also compromises data security. The problem is to analyze and address IQ imbalance to enhance the accuracy and maintain the reliable performance in OFDMA networks.
I'm Izalia, and I will present about the research question, which is the development and answers. For the first question, how does the implementation of FDMA, TDMA, and CDMA influence throughput in high-density urban environments? For the FDMA, which is the frequency division multiple access, users are allocated different frequencies within the available spectrum. Then, throughput is limited due to fixed channel allocation. And lastly, inefficient spectrum usage in high-density urban areas. And for the TDMA, which is time division multiple access, users are allocated different time slots on the same frequency channel. Improved spectrum efficiency, congestion in high-density environment leads to limited throughput. And lastly, fixed time slot allocation can cause potential collisions. And for the CDMA, which is code division multiple access, which is multiple users share the same frequency band with unique codes, greater throughput in high-density urban areas, efficient use of the available spectrum with simultaneous transmission, and least interference among users. For the second question is, what are the latency differences between FDMA, TDMA, and CDMA in handling real-time applications such as video conferencing and online gaming? For FDMA, users are allocated dedicated frequency channels. Latency is generally low latency, and channel switching and handover process can introduce delays. For TDMA, users are assigned time slots on the same frequency channels. The moderate latency due to waiting for assigned time slot, can be problematic for real-time application, especially with non-dynamic slot allocation. And the CDMA, multiple users share the same frequency band with unique codes, and the latency for CDMA, which is the higher latency compared to FDMA and TDMA, complex encoding, decoding process increased delay, and advancement in the CDMA technology have reduced delays, making it suitable for many real-time applications. For the third question, which is, how do FDMA, TDMA, and CDMA compare in terms of energy efficiency for battery-powered IoT devices? For FDMA, the latency, generally low latency as each user has a dedicated frequency channel. Channel switching and handover process may introduce some delays. For the TDMA, the latency, moderate latency due to the need to wait for an assigned time slot, problematic for real-time application if time slots are not dynamically allocated. And for the CDMA, the latency, higher latency compared to FDMA and TDMA due to complex encoding and decoding. Recent advancements have minimized delays, making CDMA suitable for many real-life applications. And the fourth question, what are the key factors contributing to the differences in energy consumption among FDMA, TDMA, and CDMA in a mobile network? So for the FDMA, factors contributing to energy consumption can fixed frequency allocation may lead to inefficient spectrum use and increased power consumption during ideal periods due to lag in dynamic allocation. And for the TDMA, factors contributing to energy consumption, time slot allocation and synchronization overhead, and devices turn on and off during their assigned slots, consuming power during transition. And lastly, for CDMA, factors contributing to energy consumption, which is complexity of encoding and decoding processes, capability to support multiple users simultaneously, and lastly, efficient spectrum usage, which can influence overall power consumption. And for the last question, which is, how do frequency reuse and interference management techniques impact the performance of FDMA, TDMA, and CDMA in terms of throughput and latency? For the FDMA, frequency reuse is limited flexibility due to fixed channel allocation, and interference management is higher interference and reduced throughput requires effective interference management techniques. And for the TDMA, frequency reuse is more flexible compared to FDMA, allowing better spectrum utilization, and the interference management challenges include managing interference and synchronized time slots, which may degrade performance. And lastly, for the CDMA, frequency reuse is inherently supported as multiple users can share the same spectrum, and the interference management spread spectrum technology reduces interference and provides better throughput and lower latency compared to FDMA and TDMA. And I will pass to the next presenter.
I'm Vaidran. I'm going to present about analysis and discussion, detailed comparison of the literature and proposed future work. For the FDMA, we want the hybrid normal FDMA assisted dual computing offloading, the latency of minimizing approach. This study focuses on minimizing latency in FDMA by integrating non-orthogonal multiple access, called NOMA, for dual computation offloading. And hybrid approach can significantly reduce latency in high-density environment by optimizing resource allocation. The second one is a resource allocation for the IRS system, wireless power FDMA IoT network. It's a finding in corrupting intelligent reflecting surfaces IRF and wireless power transfer and can enhance resource allocation in FDMA and IoT network. Advanced technique like IRS can improve throughout and energy efficiency, making FDMAs more suitable in IoT application. For the TDMA, the first one is improving the tracking accuracy of the TDMA based on acoustic indoor position system using a novel error. The error correction method can enhance the by tracking accuracy of TDMA based on positioning system. Addressing error in time slot allocation can improve the overall performance and accuracy of the TDMA system. The second one, performance evaluation of hybrid distribution centralized TDMA in high density circular network. The hybrid approach combining distributed and centralized TDMA method can improve performance in high density vehicular network. Hybrid TDMA approach offers better scalability and efficiency, particularly in a dynamic environment like vehicular network. For the CDMA, joint CCI mitigation and power control for the MCDS CDMA in LEO satellite network. Effective code channel interference CCI mitigation, power control, and can enhance performance of the multi-carrier direct sequence CDMA in low Earth orbit or LEO satellite network. Advanced interference management techniques are crucial for optimizing CDMA performance in satellite communication. The second one is a low complexity decoder for the overloaded uniquely decodable synchronous CDMA. Its low complexity decoder can improve the performance of the overloaded CDMA system, making them more efficient. Simplifying the decoding process can reduce latency and power consumption in CDMA system. For the OFDMA, the first one is load management, power and admission control in downlink cellular OFDMA network. The effective load management, power control, and admission control strategy can ensure the performance of orthogonal frequency division multiple access called OFDMA in a downlink cellular network. Proper resource management is a key to optimizing throughout and energy efficiency in OFDMA system. The second one is security analysis of uplink IM OFDMA system in presence of IQ imbalance. Addressing in space and quadrant in IQ imbalance can improve the secrecy and overall performance of uplink OFDMA system. Then the next one is enhancing security measure is essentially for maintaining reliable performance in OFDMA network.
I'm going to explain the proposed future work. First is hybrid multiple access technique. First is algorithm development, focus on dynamic resource allocation strategies, consider user demand and real-time network conditions, aim for optimal performance across multiple metrics, latency, throughput, energy efficiency. Second is intelligent reflective surfaces, in short form IRS. First is integration with the multiple access method. Develop effective IRS technique for use with FDMA, TDMA, and CDMA. Improve resource allocation, coverage, and energy efficiency. Second is algorithm design. Create algorithm for automatic IRS configuration. Consider real-time network conditions to maximize signal reception and minimize interference. Third is power optimization. Explore IRS capabilities to reduce power consumption. Optimize signal paths to achieve minimal high transmission power. And the fourth is practical deployment challenges. Address hardware design and deployment strategies. Focus on cost effectiveness for large-scale IRS deployment. Next, error correction and interference management. There are 4. First is error correction techniques. Propose new error correction codes, enhance error detection and correction capabilities, minimize complexity and latency. Second is interference management methods. Develop techniques to mitigate co-channel and adjacent channel interference. Ensure clear communication channel at higher data rates. Third is adaptive algorithm. Design algorithm that dynamically adapt to changing interference patterns. Preserve optimum network performance in varying conditions. And the last part is a cross-layer optimization. Integrate physical, MAC, and network layers to improve error correction and interference management. That's all from us. Thank you.